Answer is 5.61, which I don't have a clue. Is that the same thing as 4 plus the natural log of 5? Okay, so it's close enough. It's approximately that. But this is your exact answer that we have there. Okay, that's our process of doing that. Well, let's go on. Find the area of the region bound by. I'm going to move this out of the way so we can actually do it ourselves. Whoops, move that out of the way. There we go. Bound by this curve and y equals 0. Now, to get an idea about this curve, and again, if you think about this without using your calculator, we have an upside-down parabola, okay, concave down parabola. How do I know that? Well, the leading coefficient is negative. And if I look at this and factor out an x, I would have negative x plus 3, and I'm trying to find the zeros of that. I need to know, remember, we're talking about keeping the area above the input axis, and this parabola is going to go, you know, something like this, and I need to know where are the points that it intersects the input axis. I can find those if I set this equal to 0, and I have it at 0, and it's at 3. So I now know the area I want. How do I write that as a definite integral? Zero, 3. And what is my integrand? My function. Yeah. Again, some of you stumbled on this Tuesday, so don't forget, we're graphing the function. We're graphing the function, so that becomes our integrand. If I want to now solve this, and by the way, where's y equals 0? Otherwise known as the input axis. Okay, so we've got this whole thing. We know that we're looking at shading in this area right here, and so we want to find the antiderivative. Negative x squared. Antiderivative would be. I'll give you a moment to think about it. And the antiderivative of 3x. And again, make sure you put that in parentheses. If you don't, you're not expressing the same thing that that we are trying to work on here. Okay, so that's the curve we're looking at. Let me just. Okay, obviously it's not going to cover it up, so we won't bother with that. And then I'm looking for, f of, and always go from the top, the greatest, down to the lower bound. Actually, one step in here first we might want to do is maybe resolve that. You probably have that resolved as x cubed divided by 3 plus 3x squared divided by 2. Now we want to put that value in, and move that out of the way a little bit. So we'd end up with, let's see, negative 3 cubed, negative 27. Did we do this one? It sounds so familiar. I think what I did this in the business calc class. That was the same example for them on Tuesday. Okay, that's why it sounds familiar. Remember, you're putting f of antiderivative of 3 in. You don't jump over to the 0 until you've got this entire function rewritten with the input of 3. Then, I don't think we probably even need to show this, but we'll show it anyway. The second half just becomes 0. So we've got negative 27 thirds plus 27 halves. 27 thirds is 9, so we have negative 9 plus 27 halves. Negative 18 halves plus 27 halves is how much? 9 halves. And I think I had this, yep, there it is. From last spring, I still had the 1 there, so we could verify, and it is, in fact, 9 halves. Okay. Well, we're going to look at this thing called the mean value theorem. The mean value theorem. Okay. What's the mean? Another word for mean, mathematically speaking? Average. Okay. Do we have a mean value theorem for derivatives? Okay. And that said, remember that one said, let's go back and review here. Mean value theorem for derivatives stated that if you have a curve, and you know that if this is A, and this is B, and you know that you know those input values, and you compute the average rate of change, slope of the secant. What's the rest of it? Okay, there exists, that's a symbol we can use for there exists, an input C such that the average rate of change, that little backward E is such that, the average rate of change is the same thing as the instantaneous rate of change. Average rate of change, another way of talking about that, very simply is slope of the secant, okay? Slope of the secant, and instantaneous rate of change is the slope of the tangent. So somewhere in here, there is a point somewhere where the slope of the tangent has the very same value as the slope of that secant. That's the mean value theorem for derivatives. We're looking now at the mean value theorem for integrals. Let's see what it says. Our good old function is continuous in a closed interval, okay, a, b. It says, then there exists a number c in that interval such that. Now, let's kind of tear this apart. What do we know about this? Well, let's put it in yellow. What do we know about this? What's another way now that you know to, you know, you're not going to call it the definite integral. You can now call it the, what's it compute? Not when you have a to b. The what? Area under the curve, okay, f of x from a to b. So this now is our, we know this to be our area under the curve. Okay, well, let's take a look then at what does this indicate? Are you sure?
I'll use on C.
What? That whole thing. Now, if it's the area under the curve, it'd have to be the limit of infinitely many, the summation of infinitely many rectangles. Do we have infinitely many rectangles indicated here? No. We don't. We don't have the summation, we don't have the limit and all that. But what we do have, f of c, how did we use that f of c in our limit definition? It computed the what of the rectangle? Okay, let me see if I can help you out here. If I've got a curve over here and I've got this as c, and I go up here and I draw a line, if I'm going to build a rectangle based on that, that would be my what of the rectangle? The height, okay? So this is my height. Okay, so this would be the height of the rectangle. What would b minus a be? The base. The base. So in other words, if a goes from here to here on this curve, I'm building a rectangle, right, that has the base a to b, and what's the height of the rectangle? C. So I would come up here, go across, and then come back down. So the height of the rectangle is based on this. So there's a, do you get what this is saying? There's a point in that interval where if you build a rectangle based on the height at that point, now that value C could be way over here by B, or it could be way over here by A, it could be in the, we don't know where it is. But there's a point between A and B that if you build a rectangle based on that height, using the entire interval, you got the same area as what? Same area as what? The area just under the curve. Now, what happens is this. I didn't draw you maybe as good a picture as I could, so let me try this one more time. Here's A, here's B, and let's say that we have a curve that goes like this. Okay? So I'm going to go from here to here. And this piece says that the area under the curve, okay, all of that, this piece says that there's some point between A and B, and let's make that right here, and I'll put it in a different color so we can see it. A point right here that if I go up to the curve, okay, and I build a rectangle based on that, that area of that rectangle is the same as what? The area under the curve. That's what this is saying. Okay? Just like over here we said that if we can, that we've got a point in there, we got a point C in there whose derivative is the same, the instantaneous rate of change is the same as the average rate of change using the endpoints of the interval. That's what this is saying. Isn't that kind of neat? Who would ever think this stuff up? Well, I didn't, you know, some mathematicians years and years ago, and we just get to use their information. Okay, so that's what this is saying. Now, yeah, let's go on. Let's go on here. Find the value of C guaranteed by the mean value theorem for integrals for this function over the interval 1 to 4. Find some value. C is going to have a value between what and what? 1 and 4. So what we know is that we've got 1. Whoops, let's change the pen back. We've got 1 is less than or equal to C, less than or equal to 4. Okay? I don't know where C is. Don't have a clue. Don't know. But find the value C for which this situation, so go back and put that as with, so that this situation is true. Do we know A and B? Okay, so we're going to talk about the integral from 1 to 4 of what? 5 minus, okay, 5 minus 1 divided by x. Am I done? Dx, okay. And that has to have the same value as what? F of C times 4 minus 1 or 3. Okay? So, we've got, let's see. We've got, well, let's work on this side. Can we rewrite this? It's going to take a little bit of work, isn't it? Got to find the antiderivative of this. This is going to be, let's see, the antiderivative of 5 is, do you have that in your head now? 5x, okay. Minus the antiderivative of 1 divided by x. We just did it, so it's natural log, okay, natural log of x. Don't forget, put parentheses around it, integrate from 1 to 4. I'm going to keep all of this on the